All right, advanced math A, here we go. We got lesson 8.2.2, curved best fit models. So back, what was it, like unit 4 or something like that? We did the LSR, least squares regression line, LSRL. We did the least squares regression line, which is where we took data and tried to make it fit to a line. This time, we're going to see, can we do that same process, do a regression equation with curved models instead, like exponential models that we've been doing? And the answer is yes, of course we can. Otherwise, I wouldn't make this video in the first place, I guess. Anyways, we got 8-103. We're going to go back to the dry ice problem. Julia, his dad had like a restaurant or something. I can't remember. But he used all his dry ice to keep glasses cold. I guess that's the thing. I don't know. Maybe. So she went out and looks like she stayed up until 10 at night weighing dry ice, because that's what Julia does. That's the kind of kid she is. Anyway, so we got all this data. It's data we've used before. So in Desmos, what we're going to do is we're going to create a scatter plot of the data and look at the LSRL for it. All right, so I've already entered in the data because I'm a nice guy. So let's look at the data there. So here's all of our data here. Remember, you do the table button where you add an item up there and then make a table to do that. So anyways, that's what I did. I made a table. Here's noon, and then until 10 o'clock at night, she's just weighing dry ice. Okay, so this is our data right here. And what we're going to do is we're going to look at a least squares regression line. And so here's a least squares regression line. And it looks pretty good. I mean, it goes through the data pretty well. All the points are really close to it. And look at our parameters there. Our m value, which is our slope, is negative 0.52. Great. Our b value, which is our y-intercept, is 15.2091. Everything's looking pretty good. Okay, we've got a good equation. And look at our r squared value. Our r squared value was 0.9958, which is pretty darn good. Okay, so let's fill in that information over here. Let's go to this. All right, so let's fill in that information. We've got an r squared value. I got to take it over to here. R squared value. I can't do this on a separate screen. I'm just going to do it right here for right now, and then I'm going to show you what I wrote down. Okay, our r squared value is 0.9958. So 0.9958. I'm filling that in on my little paper here. And then our regression equation is y equals negative 0.52. Because we've got a decreasing function here, x, and then it's plus 15.2091. All right, now we can get back to what we're doing. All right, so there I've got my regression equation. We saw that the line fit the data pretty well, and we got an r value of 0.9958. And what does the r squared value mean? Remember, the r squared value is a percentage. This means that 99.58% of the change in our weight of our dry ice can be attributed to the linear relation with the hours. Okay, so 99.58% of the change in weight can be attributed or is caused by, I don't know how to spell attributed, is caused by the linear relationship with time. I was going to say time or hours. All right, so that's looking pretty good. Now let's look at a residual plot. We're going to sketch what our residual plot looks like. So let's go back to the problem. So let's do a residual plot, and Desmos does it for us, which is really nice. So we've got the residual plot. It goes down here and then back up here. So if I'm going to sketch it on your paper, so just go over to your paper and sketch it real quick. All right, so there's the residual plot that I just sketched. Doesn't have to be perfect. So what does it show? It shows that we start off with some of the points above the line, but then they go below the line, then they go back up. And we said back in Unit 4 that we really don't like this. We want it to be more random than this. So that usually means that there might be a different equation out there or a different type of equation that models the data a little bit better than what we've seen here. So what does the residual plot show? It shows that in the middle, the points are below 0. So we get a bunch of negative residuals. We start with positive residuals, we go negative, and then we go back to positive residuals. Usually don't like to see that. We want to see it more spread out and random. So we see that there's a slight pattern. In the residuals. And generally, we don't like to see patterns in our residuals. So what we're going to do instead is see, okay, is this data better as an exponential function instead? So let's go back to our data. So now we're going to look at it and say, okay, let's get rid of this one right here. So I've taken away the line. And now what I'm going to do is make an exponential equation. Well, remember how we did y1 tilde mx1 plus b? Well, now we're going to use the exponential equation where our variables of y1 and x1 are still there, but now we're going to use the parameters of a and b. So we're going to do y1 tilde ab to the x1. All right, so let's see what that looks like. Okay, it fits them pretty well. Let's look at our R value. Our R value is now 0.9984. What was it before? 0.9958. That's a little bit better of an R value. I mean, it was already really good, so I really wouldn't have complained about that one. But by using an exponential equation to do a regression model, I'm getting a better R squared value. So this is saying that 99.84% of the changes in our weight is due to time, which is better than 99.58. I mean, they're both really good, but this one's a little bit better. Okay, let's look at our residual plot. Our residual plot also looks a little bit better. Some are below, some are above. It looks a little bit better. There's not a lot of change between the previous one, but like I said before, it's only a slight difference. I probably would have been okay with the linear model on this one, but a exponential model fits a little bit better in this situation. And there's our model. So it's saying that our y-intercept, our a parameter, should be 15.3735, and our b, which is our multiplier, is 0.959492. Remember, when that number is below 1, we're going to get a decreasing function, which is why this one is decreasing over there. All right, so we need to write down on here, what does the R squared and the residual plot indicate? So let's write that down on the paper. So the R value is slightly better. So the R squared value is slightly better. And the residual was slightly better distributed. The distribution was slightly better. Okay, not a lot of difference between those two, but we got a regression equation. Oh, I forgot to write down the regression equation. Let me grab that real quick. All right, so there's our exponential regression equation. So in the form of y equals ab to the x power. So we got two different equations there. They were both really good. I mean, let's not knock the linear equation. It was a really good equation. The regression equation for exponential is slightly better. Okay, so we'd probably use this one over the other one. All right, next problem, which is our last problem for this one. All right, so this chart is a list of the amounts of oil produced from 1905 to 1972. And MMBBL stands for million barrels of oil. How much is in a barrel? Why don't they just call it gallons or something? I don't know. Are they using the same size barrels? Maybe. I'll have to look it up. Anyways, so we got all this lovely data, and it stops at 1972, and there's a reason why it stops at 72, but you'll have to look at the history books to know why that stops in 72. We were right before I was born. So, yeah, so this data goes through 1972. Things change after 72, but for right now, this is what's going on. All right, so we've got all this lovely data, and we're going to create a scatter plot for it. And because I'm a heck of a guy, I've already made the scatter plot for you. Here it is in Desmos. So I've got all my data here. My X's, I didn't do like 1905, I just put 5. So these are all the 1900s. And then over here, these are millions of barrels of oil, I guess, sucked up from the ground. I don't know what the terminology is for that. Okay, so would a linear model fit this? No, that doesn't look linear at all. My stupid lights went off. Okay, there they are. So no, linear model looks horrible for this. You know, how could we make a linear model fit that? That doesn't look great. That definitely looks more exponential than linear. So I'm going to say, nah, I'm not going to do a linear model. I want an exponential model instead. So, let me write it down on my paper. What type of model will fit the model well? I think an exponential model. Exponential. And we'll use y equals ab to the x power. All right, so I've already done it ahead of time over here. I've got y1 tilde ab to the x1 because I think a exponential model is the best fit. So I'm going to hit this little button here, and there it is. And we can see here that over here it's a little bit above it, then it kind of goes below it, then it goes above it. Not perfect, but I'll take it. It looks pretty good. Let's look at our R-squared value. Yeah, R-squared value is 0.9981. That's pretty darn good. So what's our regression equation? Well, here's our parameters. A, that's our y-intercept, and B, that is our multiplier. So we would do y is equal to 133, sorry. And then the B value, the multiplier is 1.07389 to the x. All right, so this is what we've got so far. We've got that it looks like it should be exponential in the form of y equals ab to the x. And then we're going to create the regression equation. So here's our a value, and here's our b value. Okay, so that's what it looks like. And now we're going to make a residual plot and sketch it on our paper. So let's go back over here, and we're going to do a residual plot for this. Okay, I'm going to pull it up a little bit so we can see our residual plot. So let's do our plot. And there's our plot. We got some of it going above, some of it below. We got a little bit of craziness going in there. Does it look perfect? Not perfect, but looks pretty good. Okay, so let me sketch it real fast on my paper, then we'll talk about it. All right, so I've copied it onto my paper. Kind of looked like that. Okay, that's not perfect, but yeah, let's just go with it right now. All right, so let's look at that. So is an exponential model appropriate? Well, you know what? I don't like the look of our residual plot. It almost looks like it's going woo, like doing a little sine wave or something. But you know what? This is data, and data is never going to be perfect on these things. So when you get with data, you're going to have to ask yourself, there's multiple things to look at. Number one, let's look at these residual actual numbers. They're not huge for the numbers that we're dealing with here. They never get really big. Like there's no really like huge variance in our residuals. Some of them are above, some of them are below. Yes, it looks like there's like a slight pattern going on right here and then maybe dipping down below and coming back up. But you know what? At the end of the day, with a 0.9981 R squared value, I'd probably just accept this as it is. It's not perfect, and with data, you can't expect perfection. It's not going to look like a textbook example, especially when you are dealing with real world scenarios. They're never going to come out nice. So at some point, you have to just go, am I okay with it? Yeah. I mean, we could try to make another equation that's going to fit it a little bit better, but how much better can we get than 0.9981? I mean, we could get probably a little bit better like we did on the last one. But if you were a researcher, you'd probably be happy with this, even though there's a slight shape to your residual plot there. But since a lot of these points there aren't really far off, you'd probably just accept it at some point. So is exponential model appropriate? Well, the residual plot, there's a slight shape to it, but we'd probably accept it because the residuals don't ever get really big. I mean, they get up to 414. We might think that's pretty big, but these numbers go up to 18,000. And so as a percentage of a difference, it's not a huge difference that we're looking at. So we would probably accept this and just move on with life. So is an exponential model appropriate? Sure, it's appropriate. It fits the data. Is it the most appropriate? Maybe not. I don't know. I bet we could come up with another equation, another different model equation that would work. But for right now, sometimes with statistics, you just go, you know what? This is good enough. We're going to go with it. Nothing's going to be perfect, which for math people is a little bit hard. So that's why statisticians are a little bit weird. But anyways, is the model appropriate? Yes and no. Yes, the curve looks like it fits the data. And the residuals are pretty close. So the residuals, there's not a lot of variance in like the size of the residuals. And the residuals don't show large fluctuations. That's probably spelled wrong, but I don't care. And your disagreement for this might be, no, there's a little bit of a pattern in our data. No, the residual plot has a little pattern. But I think the yeses outweigh the nos in this situation. Okay, so this is just, we're just going to go with it. So anyways, that's all I got for you. Math hard, that's all.